Chapter 28 is going to tell us all about DC circuits. DC stands for direct current. And in a DC circuit, you have a constant supply of current that stays the same. This is contrary to something called an AC current, which stands for alternating current. In an alternating current, your current flips between positive and negative. And what we're going to focus on today is talking about direct current. What we need to remember when talking about direct current is what current it actually is. If we remember, current is defined as the flow of positive charge and this is a little bit weird because the positive charge actually doesn't move. The only thing that moves when current flows are the negative charges. So if we draw a battery with a positive terminal and a negative terminal, and we connect the sides of this battery, connect a wire going from the positive all the way over to the negative. If we look at the direction that the current goes, that's the flow of positive charges. The positive charges want to move away from the positive and towards the negative. So the current is going to flow from positive to the negative. Our current is going to go from positive over to negative. So that's the direction of our current. The charges themselves, the actual charges that move, are going to be the electrons, the negative charges, which are actually going to go from negative to positive. So that's the actual flow of charge. And in essence, this means that the charge is flowing from the negative terminal to the positive terminal. In other words, it goes from a low potential to a high potential. And there needs to be some way that it gets enough energy to go from a low to a high potential. And that energy turns out to be something called the EMF. The EMF is short for something called electromotive force, and it is the energy per charge that you get from a battery. It is the energy inside of the battery that allows the charges, that allows the electrons to flow from a low potential to a high potential. EMF we describe with this little curly E, and the units, since it's energy per charge, are joules divided by coulombs, which should look familiar. We should recognize that as being equal to a volt. So the voltage measurement, the voltage that you see on batteries, actually tells you the EMF of that battery. And when we're talking about the EMF inside of a battery, we need to remember that the energy gained inside of a battery, the energy that the battery uses, has to balance with the energy that you expel through a wire. Because that's really the purpose of hooking something up to a battery. You want to make that energy flow through the wire. So the energy inside of the battery has to be equal to the energy that goes into that wire. We write this in equation form as the EMF, curly E, plus the change in potential inside of the wire is equal to 0. The energy in the battery, E, is given to the energy in the wire in terms of a potential, and that adds up to a 0 total change in energy. So the primary focus of this chapter is going to be to analyze these EMFs and how they work in terms of circuits. So let's say I have a circuit. Let's say my circuit is for a flashlight. Here's my flashlight. Flashlight has a switch to turn it on and off. It's got maybe 2 D-cell batteries inside of it. And we've got a light bulb that produces some light that actually makes the flashlight work. Now I'm going to redraw this flashlight in terms of a schematic diagram. And I'm going to use symbols that we've already grown accustomed to for some cases. The light bulb acts kind of like a resistor. It resists some flow of charge. So I'm going to draw a resistor that represents my light bulb. I have 2 batteries. Remember, battery is a long line for a positive terminal, short line for the negative terminal, and I have 2 of those. Then I come around and I have my switch. Switch we draw with a little diagonal line, and then finally I close my circuit. I can label what all these things are. The little resistor is my light bulb. These 2 guys over here are the batteries, and I have a switch. We're going to use these kind of schematic diagrams in order to analyze circuits. And we're going to have 2 different rules that we use for analyzing circuit diagrams. These are called Kirchhoff's laws. The first one we're going to use is Kirchhoff's voltage, or his loop rule. And this tells us that the sum of voltage in a closed loop is 0. And to apply this loop rule, we have a few steps. The first step is to pick a direction for the current to move. We'll do an example of this. I'll show you what I mean, but you need to pick a current direction. Doesn't matter what you pick, you just pick one. And once you do this, you actually draw a loop. You draw a loop around your circuit, and if you pass in a battery from the positive to the negative terminal, then you're decreasing your potential. You decrease your EMF. Conversely, if you pass from a negative terminal to a positive terminal, then you're going to increase your EMF. Then, final 2 steps of the loop rule. If you pass a resistor in the same direction as your current loop, then your voltage drops. Then voltage drops according to negative I times R, Ohm's law. And finally, if you pass a resistor opposite to current, then you gain some potential. and that potential gain is V equal to positive I times R. Okay, you have to learn all these rules, keep them in mind, you'll get some practice with them, and let's look at an example to see what they actually practically mean. Let me just draw some kind of simple circuit. I'm going to draw a circuit with, let's take one battery. I'm going to call this EMF number 1. And I'm going to go through a resistor in my circuit. And then I'm going to go through another battery. Next, I'm going to go through another resistor. And another resistor. And finally, I'll go through one more battery. I'll label each of these pieces. So I have first, my first battery is E1. My first resistor I'm going to call R1. Then I have another battery. I'm going to call that E2. And then my second resistor, an R2. And then my third resistor, an R3. And finally, my last battery I will call E3. And the first step in the Kirchhoff's loop rule is to pick a direction for my current. So I'm just going to pick whatever direction I want for my current. And I'm going to pick clockwise for my direction for my current. So that's the direction that my first current goes. And I only have one current because I only have one wire, so my current's going to go clockwise throughout this whole circuit. This is the direction for my current throughout this entire circuit. And the current is I1. Next, I need to pick a loop. I need to draw a loop for the direction that I'm going to go through my circuit. I'm going to start my loop right here on the negative terminal of this first battery, jump over to the positive terminal, and I'm just going to draw a loop that goes, again, I'm going to pick that direction to be clockwise. I don't have to. I can pick whatever direction I want, and I'm just going to call this my first loop. And then what I need to do is start adding up how I'm moving through this circuit. What kinds of things are changing. So, if I pass through my first battery, I look at how I'm going through my first battery in my loop. I'm going from a negative terminal to a positive terminal. And in that case, that means that I'm increasing my voltage. If I pass a battery from the negative to positive terminal, my EMF increases. Then I keep going, and I'm going around my loop. I'm going clockwise, and I hit this first resistor. I pass through this first resistor going towards the right, and I look at my current. I chose my current to also go right. Since my loop and my current are going in the same direction, this means that for my R1, that's going to be negative. The loop is going to the right, and the current is going to the right. So that means I have a negative voltage change. My V through my first resistor is equal to negative I1, the current through the first resistor, times that first resistor. I keep going around my circuit. I'm going down. My I1 is going down. It's going from the positive terminal of a battery to the negative terminal of the battery. So that means that my E2 is going to be negative. I'm losing some voltage. I look at my R2. If I look at my R2, I'm going clockwise through my second resistor, and my current is also going clockwise still. So my R2 is going to give me a negative I1 times resistance 2. And finally, I look at R3. My current and my resistance are going in, my loop and my current are going in the same direction through this resistor, so I have a negative I1 times R3. I have a negative voltage drop. And finally, my E3, I am going from a negative terminal of a battery to a positive terminal, so I'm increasing. I have a positive increase in my voltage. And the real essence of Kirchhoff's law, Kirchhoff's first loop rule, is to add up all of these results to get a final loop around this circuit. I'm adding up all the voltages around my circuit, and they have to be equal to 0 according to Kirchhoff's law. So if I sum up all of my loops, all of my currents, and all of my voltages, all of my EMFs, my first battery was passed from a negative to a positive. So that's going to be a positive increase in my EMF. Then I pass my current in the same direction as my loop, so I'm going to decrease my voltage according to I1 times R1. That's the voltage drop across the first resistor because the current and the loop go in the same direction. And then my second battery, I'm going from a positive terminal to a negative terminal. So that means I have a voltage drop across my second battery. My third resistor, I'm still going in the same direction as my current, so I still have that voltage drop. Third resistor, same thing. Current and resistance loop is going in the same direction, so there's a voltage drop. And then my final battery, I'm going from a negative to a positive terminal, so I'm increasing my EMF. This total loop gives me all the voltages across my entire circuit, and that sum has to be equal to 0. And just to be very, very clear, these I's times R's, these all come from Ohm's law. And if we remember Ohm's law, V, the voltage drop, is equal to I times R, the current times the resistance, which is exactly what we have here. It's exactly what we're calculating with Kirchhoff's loop rule. The sum of voltages has to be equal to 0 for a closed circuit loop. So we might have a case where we get a circuit that looks a little weird. Here's a battery, and we come in and we reach this place where we can split into two different resistors. This type of multi-loop circuit where I have two different places for my current to go. As I'm going through the circuit, my current has a choice. It can go right or it can go left at this point. Now the easiest way to deal with this would be to simplify this circuit. Resistance 1 and resistance 2 are in parallel. So I can find the total resistance of these two if they were just one resistor. I know that 1 divided by the total resistance is equal to 1 divided by the first resistor plus 1 divided by the second resistor. This is how we add resistances in parallel. So I can add these two together like so, and I can simplify this circuit so that I don't have current getting split up. And I simplify this circuit so that my R1 and R2 become one equivalent resistor. We'll call that R total. So I use the approach to add resistances in parallel to simplify R1 and R2 into some R total, some equivalent resistor, and I can work with my circuit in this easier way. But occasionally we get tougher circuits. We could have a tougher circuit where we have a battery and we have a little choice for that battery, for the current that comes from that battery, to go in a couple different directions. And then to make it even harder, we'll just add in another battery. So there's no way that I can combine these two batteries or that I can combine this resistor with anything else to force the current to go through in one direction. No matter what, my current in this circuit is going to have to split up once it reaches this place. We call this place a junction. So any current that comes out of this battery and reaches this junction, we'll call this the first current, has to get split up into a second current and to a third current. It reaches this divide and it has to choose a path. This is where Kirchhoff's second rule comes in. So Kirchhoff's second law is called Kirchhoff's current or junction rule, and this one's a little bit easier. This tells us that the current that flows into a junction equals the current that leaves a junction. So our general approach to do these circuit pictures, circuit diagrams, is going to be first to draw currents. And we're going to draw currents so that they obey the junction rule, obey the current rule. Current into a junction has to be equal to current out of a junction. Then I'm going to draw loops. According to the loop rule, and then I'm going to apply the loop rule to figure out how the voltage is acting through my circuit. So let's look closer at that circuit that we couldn't simplify, that we couldn't add resistances in. So the first step we're going to do is to pick currents and identify current directions. Now I have different places that the current can go because I have these junctions, these places where the current can split. So I like to mark my junctions with a little dot. That means that I know that the current splits at these points. And I can pick directions for all my currents and identify currents. Now in this outer portion, on this left-hand side of my circuit, I'm going to say there's one current that goes through that. I'm going to call that I1. Now once I1 reaches this junction, it's going to have to split up. So my I1 comes into this junction and splits into two different currents. I can have a current that comes out. I'm going to call this I3. Current that goes into the right-hand side of the circuit. And then I have a little bit of current that can go down through this middle part. And I'm going to call this one I2. So these are the two currents that I can have. And according to the loop rule, I know that the I into a junction has to be equal to the I out. Current in is equal to current out. The current that's going into this junction, the arrows that are pointing into this little red dot, that's just I1. I1 is the only current that's going in. That has to be equal to the current that goes out. The current going out, the arrows that are pointing away from this junction, are going to be my I2 and my I3. I can see there's no arrows pointing into this junction for I2 and I3, so I know they're going out. I2 plus I3. And I've done my loop, I've done my junction rule. Now I need to pick some loops and draw those in. So I'm going to pick a loop number 1. I'm going to start at the negative end of my battery, jump to the positive end, and I'm going to loop around this part of the circuit. And then I'm going to pick a second loop. I'll label this my first one and my second one. I'm actually going to start at the positive side of the battery, jump to the negative side, and I'm going to loop around counterclockwise, or clockwise. So those are my two loops, loop number 1 and loop number 2. So what do the voltage drops look like for these two loops? For loop number 1, I look at where I'm starting. I'm starting at the negative side of the battery and jumping up to the positive, so I'm increasing by a voltage amount E1. So I have a positive E1. I continue around my loop and I reach this first resistor. I'm going down through the resistor, and the direction I chose for my current through this resistor is also down. And the current flowing through this is I2. So since my loop and my current are going in the same direction, this means I have a negative drop in my potential. I have a negative I2, the current that is in the actual branch that my resistor is in, times the resistor, R1. And if I finish off my loop, I get back to where I started, so I know this loop is equal to 0. Then I can do my second loop. My second loop. I start at the positive side of my battery and jump to the negative side. So that means I'm decreasing my potential EMF through this battery. So that's going to be a negative E2. I keep circling around. I'm going up for this loop through my resistor. My current is going down. That's the opposite direction. My loop is going up. My current's going down. So this means I have a positive increase in my potential. So I can add the current that goes through that resistor I2 times the resistance R1 to get my positive voltage increase, and that's going to be equal to 0. And I've just completed pretty much this whole problem. Now the tricky part is to solve for whatever they ask you to solve for, and you will do that using these three different equations. Your two loops, loop number 2, loop number 1, and your junction rule. Just as a guide for when you're trying to solve circuits. So the general approach for circuit diagrams. Generally, the first thing you want to do is choose current in each part of circuit. Pick the current. You can put it in any direction that you want, but you need to choose the current in the circuit branches. And one of the most important things here is to include the directions and enforce those directions. As long as you're consistent, then your problems will always work out correctly. The algebra on these gets very messy, but as long as you're consistent, it will all work out. Once you've chosen your current directions, you need to make sure that you write the junction rule. Find out which currents are entering a junction and which currents are leaving. The total current into a junction has to equal the current out of a junction. So this junction rule is very important and uses your currents. After you have a junction rule written down, you need to find closed loops. And you will use these closed loops to write the loop rule. To get practice with this, I suggest looking at example 5. They go through some steps for you. Take a look at the problem-solving techniques on page 900 and look at checkup number 28.4. And finally, the most important part of the circuit is the purpose. The purpose is to give power to something, whether it's to light a light bulb or to heat up your toast. And the power inside of a circuit is equal to the current times its voltage. Now, I remember this by thinking of pi. But this is not the only way that we can represent power inside of a circuit, because we also know that EMF, the voltage, is equal to the current times the resistance. So we can shuffle things around and we can plug this in. We can plug this into our pi equation, so we also find that P, power, is equal to I times IR, which is I squared times R. And finally, we can also notice that P is equal to change in V squared divided by R. By plugging in our knowledge that the current is equal to E over R. So I'm just shuffling around Ohm's law. Remember, this voltage equals current times resistance is Ohm's law. Shuffle it around and I can get 3 different ways to represent the power inside of a circuit. depending on if I know the voltage, the resistance, or the current. And the way this works is very, very interesting. It's very useful. The power inside of a resistor actually heats it up. So your light bulb is actually just getting heated up by the current that flows through it. The power dissipated by a resistor heats up whatever it's traveling through. So what you're doing when you turn on a circuit is you're really converting electrical energy in the form of potential. You're taking the potential in the battery and you're converting it into heat. And that heat energy is what powers your material. And you see this all around you. You see this in toasters. If you make toast in the morning, you're just the coils inside of that toaster are just resistors that heat up when you pass current through them. You see this in heaters. This is how heaters work. You see this in hot plates. You see this in light bulbs. We see this all over the place. Power inside of a circuit.